In this video, I want to spend a little bit of time to talk about how frames will end up being allocated. So here's our first thought. What is the minimum number of frames? And I kind of already hinted at this before. Think about that for just maybe 1 second. So here, probably when we say minimum number of frames, well, there's kind of maybe two numbers, right? One is kind of in general. So based on your architecture and kind of the operations that it supports, you may need a different number of pages. The thing that I mentioned in a previous video is basically that we have, the case of an operator that takes, 3 operands. That means those 3 operands could exist at 3 different pages. Therefore, the minimum number of frames my system has to have, right, is 3 frames. Right? I need to allocate these 3 frames to every process, or it simply cannot run. That kind of can vary, right? So if I have other operands that maybe use, additional, if I have other operations that use more operands, then obviously I need to have more pages available, right? So that I can basically have a hope of getting all the data that's needed for any operation. That's something I need to take care of. Also, right, if my operations have some sort of a level of indirection, so sometimes there's something like a pointer then what that means is then in that case, right, there's a place basically to store the pointer and then a place to store the stuff that's points at. And so if I allow that, right, maybe that doubles the amount of frames I have to have available. So for sure, I'm going to have at least that much. There's maybe also another number, right, in terms of the process themselves. So if I think about the number of frames the process needs to use, right, probably, right, the process has this much program code. It's going to need this many frames to use stuff, to do stuff, right. I need to probably have that. And we'll end up actually talking about that a little bit more. There's kind of additional discussion there, right? That actually leads into the idea of thrashing. So thrashing is basically when we have this kind of cyclic thing that happens where it's I'm constantly bringing pages in and out. That happens basically when I don't have the appropriate minimum number of pages for a process. All right. So as far as allocation schemes, the first thing that people do is something called equal allocation. So in equal allocation, what we do is we look at physical memory and say, okay, we have this many frames, take that, divide by the number of processes, and give each of those processes, basically an equal number of shares, right? We split it down the middle. Well, not the middle, but split into pieces, right? Equal sized pieces. This is a bad idea. Why is it a bad idea? Ask yourself that for 1 second. Well, the simple reason why it's bad is that because processes are not the same size. So I have some processes that just take a little bit of space and some take a ton of space. It doesn't make sense, right, to give everybody the same amount, right? We don't have our provisioning be the same. Really has some dependency on the program. So how can we do it a better way? Maybe a better way would be have something like, you can think of array resizing, where it's I start with a certain amount. If I need more, I'll request more. If I don't use all the stuff that I have, I'll basically get my space be halved, right? So I can basically go up or down based on how much I actually used. So that would probably be a better approach. Another side thought here, right, is how does the equal allocation work in terms of creating and destroying a process? Basically what happens there is whenever you remove something, whenever you kill a process, you basically have to look at how much space it releases and then evenly divide it and spread it among everything it's running. That's fine, it's easy to do. Where you get in trouble though is when we create a process, because if we create a process, well then we can calculate how much size it should have, but then we'll need to go to all the other processes in our system and basically borrow from them this number of frames. So that's kind of going to be problematic, right, is if we're trying to add a new thing. So overall, right, equal allocation, right, is kind of going to be a bad idea. Typically we want some sort of a resizing thing to happen. When we're picking our page allocation algorithm, one thing we want to maybe think about is the idea basically of doing global versus local page replacement. Those are actually keywords here, right? So global page replacement, local page replacement. What global page replacement means is that when I'm picking a victim frame, I can pick that victim from anybody in the system, right? So all the processes out there are all using memory. They all have frames allocated to them. I can pick from among all of them. For a local replacement, what we're saying is when I pick a victim, it has to be within the process, right? So this process needs to bring a new page into memory, right? It needs to pick a frame. The only victim frames you can pick, right, are the ones that it already owns, right? Versus a global scheme, it can pick a victim from everybody else that's out there. So these are two different approaches. So let's think, for example, in terms of global. What are the advantages to global? Well, an advantage to global is basically going to be that if a page is available, we're going to be able to pick a very good page, right? Because I have basically the ability to look at all the pages that are out there, right? That kind of gives me more flexibility. I can definitely pick somebody that's going to be good to replace, right? So that's a nice thing. In terms of disadvantages, the problem here is I end up affecting other processes. So one process maybe has a bunch of page faults, it needs to load up a ton of stuff, ends up basically borrowing memory from another program, right? And this is a little bit problematic because maybe that program actually did need that, right? So I have sort of interference between processes. So then there's also local. What would be the advantage to local? The main thing there with local, right, is kind of a system level thing, which is, well, I don't mess with anybody else, right? So it's kind of the opposite of the disadvantage to global, right? In a local one, you can basically be guaranteed that if a program triggers a whole bunch of page faults, those page faults aren't going to interfere with the memory access time for any of the other processes that are running. In terms of disadvantages, the disadvantages, of course, kind of the opposite of global, in that a local one can only pick from a certain amount of pages, right? And those certain pages, right, may or may not actually have a good candidate for replacement. But at least you keep it self-contained so you don't affect other parts of your system. The final here, and we'll just mention this briefly, is this idea of a non-uniform memory access system. And this is basically kind of another factor to think about, right? So this whole slide here is, factors that your algorithm could potentially take into account, right, if you're doing page replacement. This slide is basically to say that, not all memory is created equal. So maybe I have things like, I have memory right on a CPU, right? So I could have a CPU, right? That has memory. I also have RAM, right? And there's some sort of a latency between it. But there's also kind of, different types of RAM. There's kind of like a RAM on the motherboard. There's RAM on an add-in card, right? And your CPU maybe can access both those sources of RAM. But then the issue is, one of these takes longer than the other. And that maybe should feed into my process. Like I need to, I don't want to, manipulate the slower memory I want to minimize the amount of time I spend manipulating the slower memory. Whenever possible, I want to be using the faster memory because, it's faster, right? So not all things are created equal. This is actually kind of for very older systems, right? So you guys probably haven't seen it, but older systems would have this basically the idea of you would have like an add-in card that had RAM in it, and that was where you had to pick up a lot of latency because it wasn't just the sticks you put on your motherboard; it would actually basically be a physical card you added. And so this is kind of some input, right, to the way you do your allocations, right? Obviously, you want to do it on the fast one if you can, right? If there's pages that aren't being used a lot, it'd be nice to have, if that was on the slower memory. For scheduling, right, obviously if a process is a higher priority, right, you want to keep that in the main memory and not have it, you'll be dependent on the slower memory. It feeds into a ton of stuff, right? So this is kind of just another idea, right, non-uniform memory access. So we've talked through basically the idea of memory allocation, right, and then some kind of different factors in playing with it. And so we kind of have some better idea now of how we kind of set up our memory management scheme.